So I'm going to talk about vectors. And the title here says everything you need to know about vectors, and that's obviously a lie. I can't tell you everything you need to know. What I am going to tell you is the stuff that you need to know to be ready for, in particular, I'm looking at the second semester of calculus-based physics course. So you're going to be looking at the electric field and the magnetic field. That's the main idea. And so this is a vector preparation for that. These are some of the things that you probably looked at before in your previous course with the physics, with mechanics, momentum, and forces and stuff. But maybe you forgot. Maybe you didn't cover all these. Maybe you saw them a little bit different way. But this is where that we need to be to talk about vectors. So what do we talk about when we talk about vectors? I just made that up. I kind of like it. Okay, so these are the things I'm going to go through. I'm telling you what I'm going to do. What is a vector? How do you represent vectors? How do you add / subtract? But we know that adding and subtracting are the same thing anyway. How do you add, subtract vectors? How do you multiply a vector by a scalar? Find the magnitude, unit vectors. This one is tough for people to understand. Dot product, you probably did this. Cross product, you may not have done that, but we need to at least mention it. Okay, so what's a vector? So what's a quantity? What's a scalar? So, you could have things like, let's say I have this box right here. And I want to measure the temperature at every single point in there. So I pick a point right there, and it's 28C. And I pick down here, and it's 27C. And I pick a point over here, and it's 15C. Why is it so different? I don't know. Maybe there's some cold thing over there. I don't know. And so each one of these points has an x and a y and a z coordinate, but they also have a temperature. And so the temperature is just one single thing. And so that would be a scalar. So T equals 28 degrees Celsius. That's a scalar value. It just has one single value. Okay, so now imagine I have another box over here. And I have points in it too. It's a box right there. And now I want to measure the speed of the air. So the speed at this point is 2.8 meters per second. That's kind of fast, but whatever. But is it going this way or is it going up? But I need to represent the direction of that. So it's 2.8 meters per second that way. Over here, it's going 2.7 meters per second, but it's going this way. That's 2.7. And over here, it's going 1.5 meters per second that way. So I can't just say 1.5 meters per second because that's obviously different if it's going up or down. So I need more information than just what the value is. I need to know what direction it is. So a lot of people say a vector has both magnitude and direction. And I mean, that's not wrong, but it's really not the best thing. A better way to think about, even though I've drawn it as magnitude and direction right there, is a vector is a variable with more than one piece of information. It's not just how fast. It's really how fast it's moving in the x, y, and z direction here. So that's what a vector is. It's a type of quantity that can have more than one piece of information. And so some of the ones that we're going to see, you've probably seen G, the gravitational field, E, the electric field, F, force, P, momentum, the torque, tau. Okay, and then in physics, the second semester of physics, you're going to see the electric field, the magnetic field. Those are the two main fields that, and force. But those are the two main vectors that I'm thinking of right now. Position, we'll definitely deal with position, R. So those are vectors. Okay, so how do we represent vectors? I've already drawn right here, but let's go back and start over on a new piece of paper drawing vectors. So the easiest way to draw a vector, since it is to represent a vector, is to draw it. Okay, if we want to say in 2 dimensions, I can represent a vector as an arrow. So I'm going to draw an arrow right here, and I'm going to call that the vector A. If we write a variable, I put an arrow over it to signify that it's a vector. So I could have A, and that's a scalar because it does not have an arrow, and this is a vector because it does have an arrow. And then I can write something like this: A equals B, right? And that's a vector equation. I cannot say A equals B because I cannot have a scalar and a vector equal to each other. It's impossible for them to be the same thing. So you can't do that. And I see that a lot. So just be careful that you don't make a scalar equal to a vector. So that's a scalar and that's a vector. So there's my vector A, and I can represent it as this arrow. So the length of the arrow represents the magnitude, and the direction of the arrow represents the direction. That's pretty easy. And if I have another arrow over here, let's put it over here, and this is the xy plane. B. If the length of B and the direction of B are the same as A, then A is equal to B, right? So it doesn't matter where that vector is drawn. It only matters how long in the direction. It matters about the arrow. We're measuring the arrow, not where it is. So that's one way to represent a vector is by drawing it. The bad thing here is that if I want to do a three-dimensional vector, that's pretty tough. If I want to do a four-dimensional vector, yes, you can have four-dimensional vectors. It's even tougher because how do you draw something in 4 dimensions? So, but that's the first way to do it. Another way to represent vectors is by describing the vector in terms of how much it moves in the x direction and how much it moves or is pointing in the y direction and how much it's in the z direction. So I can write the vector A, one way to do it, and I'm going to show you the most common ways. I could say A equals, I'm going to call this AX, x hat, plus a y hat, plus a z hat. So in this representation, x hat, y hat, and z hat are unit vectors, and we'll talk about that in a little bit. Ax is the scalar value of the projection of the vector A into the x direction. So that's just a scalar number. So this is like, this would be Ax and AY are the amounts that's projected into that direction. And you'll notice that AX and AY are perpendicular, and that's really useful, and we'll get to that. So this x hat, y hat, z hat notation is very popular. Another way that is often done is to write it like this: A equals AX I hat plus AY J hat plus AZ K hat. This is the same thing. It's just that these are people that are like, hey, X hat, Y hat, Z hat either looks confusing or not cool enough, so I'm going to use I, J, and K. So they're the same thing, except I hat is the vector, unit vector in the X direction. So you will see both of these in textbooks. Now, I like to use the version from that's popular in my favorite textbook, Matter and Interactions by Chabet and Sherwood. They probably didn't invent this, but it's still, that's where I see it. And it looks like this: A equals AX, AY, AZ. So we have an angle bracket to begin the vector, and then these three components. We don't have to write X hat, Y hat, Z hat. That's implied. This is a little bit shorter notation way to write it. But these are all the same thing. I think that's important to realize. I like to use this also because when we do things in Python, which I'm going to show you Python, it looks more like the way we would write it in Python. Okay. All we need to know is those X, Y, and Z components. So that's how those are the three most common four, really. The graphical, and then these three ways to represent a vector, but they're really the same thing. Okay. So where am I? That was how do you represent vectors? Okay, adding and subtracting vectors. Let's start by adding two vectors graphically. So let's say I have, this is the X, the Y, I have the vector A, and then the vector B. I'm going to put B right here. And so remember that the vector is the same no matter where I put it. So I can move this vector around wherever I'd like. If I put them, we call this the tip. That's the tip. Well, which one's the tip? That's the point. I tip the tail like this. Then I can draw the sum of A and B, which I'll call C. So let's call this A plus B equals C. And you'll notice that both sides of this equation are vectors, right? I have vectors and vectors, so that's good. So I could draw that a plus b is equal to c as the vector that starts at the beginning of a and ends at the end of b if they're put in this direction. So this will be the vector c. Now, what if I did b plus c? B plus c, I'm sorry. What if I did b plus a equals c? It still equals the same thing, right? So if I take the vector b, I'll put it down here. I'm going to move it. Here's my vector. Oh, I'll put it right here. What if I put b right here and then a right here? So if I do b plus a, I still get to the same place. So the order of operations for addition, of vector addition, does not matter. And then I could do a whole bunch of vectors. I could do, let's just start from here, a plus b plus c plus d, and then here's my resultant. Okay, so you can just keep on adding them up that way. But you can see if you have 2 vectors, it's possible to figure this out. If you have 5 vectors, it gets really cumbersome to do. So we don't want to do that. So let's add vectors by components. So if I have these 2 vectors, a, and let's just put this as b. So both of these vectors I can represent in terms of an x and y component. So my x component of a is going to be ax x hat right here, ax x hat. My x component of b is going to be right here, bx x hat. And then I have my y component of a right there, ay y hat. And I have my y component of b, which is in the negative direction, but that's fine, by y hat. That by would have a negative value. So I can break these, since I can represent a as the sum of these 2 vectors and b as the sum of those 2 vectors, I could say this. A plus b equals ax x hat plus ay y hat plus bx x hat plus by y hat. And since the order of operation doesn't matter, I can group these together. I can group the x's together. So I can say this is going to be ax plus bx x hat plus ay plus by y hat. And because since these 2 are in the same direction, adding them together is the same as adding their scalar values. So if I draw that out, it would look like this. ax x hat, bx x hat, and then I'd have ay y hat, by y hat, and this would be my resultant. But adding things in the same direction is pretty easy. Adding things in the same direction here is easy. And adding things that are perpendicular is easy, because we can use the Pythagorean theorem. So the answer is, how do you add vectors? You add their components. So in general, if I write 2 vectors, I'll write 3. A equals ax, ay, az. These are scalar components in the x and y, z direction. B equals bx, by, bz. And c, I'm doing 3. Cx, cy, cz. Then a plus b plus c equals the vector d. So d would be the vector ax, that's an x, plus bx plus cx, ay plus by plus cy, az plus bz plus cz. So I just add all the components. Now, you do need to make sure that if these are negative, then you're adding a negative number, right? I mean, I guess I should go back one step and say, well, what if I don't have, how do I get these components? I mean, I think the best way to represent a vector is by components, but a lot of times the vector will be represented as some magnitude 10 with some angle 33 degrees. In that case, you have to use your trig and say, okay, look, Here's my x component, ax. Here's my y component, ay. And that's the magnitude 10, so I can say ax equals 10 cosine 33, ay equals 10 sine 33. Because remember, cosine is adjacent over hypotenuse, so it's going to be ax over 10. And so you can solve for ax. Now, if you do this, be very careful about the signs of these values. This is in the positive x direction. That's in the positive y direction. So if it's in the negative x direction or negative y direction, make sure that you give it a negative component. Also, be very careful that this is cosine because that's the adjacent side, not because it's the x. Sometimes if you get the angle from up here, then the x component would be sine. So draw that triangle and represent it. I don't want to focus on that because there's a whole bunch of other great things to do, but that's how you add vectors. What if I want to subtract vectors? I'm going to run out of paper. So let's say here's the most common thing that we do. Here's the vector in the vector r, rq. This is the location of a charge, but I want to find the electric field right there, RO. I need to, that's this vector. So I need this vector R, which is from the charge to the observation location. So this is vector subtraction. So R would be the final position, RO, minus then the starting position, RQ. So if I subtract vectors, I just subtract their components. So this would be equal to, I'll write it out, ROX minus RQX, these are the components, ROY minus RQY, ROZ minus RQZ. Okay, and those could all be values. And I'm going to show you some values when we move to Python. But that's how because adding and subtracting is the same thing. I could also write this as R, I guess we should get to scalar multiplication now, because I could write this as R equals RO plus negative RQ. But then how do you multiply a negative times a scalar? So how do you do scalar multiplication? I'm totally going to run out of paper. Let me grab some more paper. So scalar multiplication. So let's say I have the vector A, AX, AY, AZ. And I want to multiply it by the scalar value A. I can say AX is going to be, if I have a scalar value and I multiply it, I just multiply each component by that value. So this is going to be AX, AY, AZ. If I want to multiply by -1, I can do that. I'm going to use an actual number. Let's say the vector B is equal to 1, 2, 3. Negative B would be equal to a -1 multiplied by the vector B. So I have to multiply this by -1, so it'd be -1. Multiply that by -1, -2. Multiply that by -1, -3. Okay, so you have to do that. So I can do scalar multiplication. I'd be very careful about units. Let's show the velocity. So the velocity is delta r over delta t. So let's say delta r is a vector 1, 0, 2 meters, and delta t is 0.5 seconds. So the velocity, that's a scalar, right? And now I'm really multiplying this by 1 over delta t, which is the same as dividing each component by delta t. So that means the velocity would be 1 divided by 0.05, so which is 2. 0 divided by 0.05, which is 0. 2 divided by 0.05, which is 4. Now, I do have units. I have meters divided by seconds. So vectors do have units. Do not forget the units. That is important. So scalar multiplication, you just multiply everything by that. Okay, where am I on my list? Magnitude. Okay, so how do you find the magnitude of a vector? So this is going backwards, right? If I know if I have a graphical representation of a vector as this, and I know the components, I know ax, x hat, ay, y hat. And just to be clear, that should be an x hat there, right? Because if I'm saying this vector A is the sum of those two sides, those have to be vectors, or it won't give another vector. But let's say I know these components. Let's say A is the vector 1, 2, 0. And it's math, so don't have units. And I want to find the length of this. Sometimes I actually do need to know that. So I can say the magnitude of a vector, we represent that with absolute value signs like that, is going to be, well, if I know the magnitude of this side, which I do because this is a unit vector, and the magnitude of that side, then this is just Pythagorean theorem. So this would be equal to the square root of 1 squared plus 2 squared plus 0 squared. It actually works in 3 dimensions. Now, if this is an actual, whatever the units of this vector, it's going to be the same as the units for the magnitude. And some people write this, the vector A magnitude as just A. And that's fine. I try to do it this way as much as possible just so we don't get confused. But that's the magnitude. You just take, in general, the magnitude of the vector A is the square root of ax squared plus ay squared plus az squared. And since you're squaring and taking the square root, the magnitude of the vector is positive. It's a positive number. And just to be clear, we don't describe vectors as either positive or negative. We don't say it's a negative vector. We can multiply a vector by a negative, but since it's in x, y, and z directions, it maybe have a negative x component, but we don't really say, oh, it's a negative vector. That doesn't make sense. What if we have this vector? This is an important one, the 0 vector, which I should have put in here. What if all the components are 0? Well, in that case, the magnitude is also equal to 0 because you square those and add them up, you get 0. And we call this the 0 vector. Okay, that is an important thing. So you'd say A, you can't say A is equal to 0. You can say it's 0, 0, 0, or you can say 0 vector. And it's important because if we have something that's 0 and you want to relate it, you have to show it's a vector on both sides of the equation. So just be careful about that. Magnitude, unit vector. This one is tougher. Okay, so what is a unit vector? Let me start with this gravitational force equation like this. If I have a planet, a gravitational field, I'm going to do the gravitational field. Yeah. And I want to find the gravitational field at some location RO, and here's the location of my planet RP. Then I need to find this. I could say the gravitational field is G equals negative G, mass of the planet, over the magnitude of R, and this is the vector R, squared. And it'd be m1, m2 over r squared if it's the force, but it's the gravitational field. But you see the problem here, right? That's a vector. G is a gravitational constant. Mass, that's a scalar, it's a scalar. Magnitude is a scalar. So I have a scalar over here. I can't have that equal to that. And why do I have a negative sign? It's because you have to put another, not that, r hat. I need a unit vector. A unit vector is a way to turn a scalar into a vector by multiplying it by a unit vector. And we already saw that, right? We already have these unit vectors. There's a unit vector called x hat, and it looks like this, 1, 0, 0. There's a unit vector called y hat, and it's equal to 0, 1, 0. And so this has a magnitude of 1, because it's only got one component, a value of 1. It has no units, but if I multiply by ay, if I multiply some scalar ay by y hat, I get a vector, right? It says it's not going in the x direction, it's 1 in the y direction, it's 0 in the z direction. But it turns out that I can do that over here too. If I want to say, here's the gravitational field that way, well, I need to know which way that way is. It depends, it's the opposite the direction of r. So I need to find the direction of r, and that is r hat. It's a vector with a magnitude of 1 pointing in the direction, that's negative r hat, in the direction of r. So how do you find it? R hat is going to be the vector r divided by the magnitude of vector r. And that seems weird, but if you work it backwards, you can see this. R equals magnitude of r times r hat. So it's a great way to represent a vector as its magnitude times its direction. And so sometimes we just want the direction, like up here. I can't, if I multiply that by r, that's going to change it, right? Because I don't want the distance up there on top. I can multiply by r and divide by r cubed, but that's a vector. So that's one way we do that. We need this a lot because you're going to see the electric field is this, 1 over 4 pi epsilon naught q over r squared r hat. The magnetic field depends on r hat. It's going to come up quite a bit. When we do electric flux, we need unit vectors there too. So it's a way to make a scalar back into a vector. And we can find it by dividing this vector by the magnitude of that vector. So let's just write that out. Let's say I have r equals rx, ry, rz. Then the magnitude is going to be this, the square root of rx squared plus ry squared plus rz. And I'm going to do an example with this. I should do it now, but I'm not going to because I don't know why. So then the unit vector r hat is going to be this vector rx divided by the magnitude right there. Let's write that out the long way. Rx over the square root of rx squared, I shouldn't have done that, ry squared plus rz squared. The y component is going to be ry over the square root of rx squared plus ry squared, that's a y, plus rz squared. And then rz over the square root of rx squared plus ry squared plus rz squared. But you'll notice that if I then go back and find the magnitude of this, everyone's going to have this thing squared in it, and it's going to have that squared on the top, so it's going to give me a magnitude of 1. That's what we want. Okay, where am I? Unit vector, dot product and cross product. Ooh, these are getting tough here. This is a little bit longer than I wanted to do, but I'm getting it all together in one shot, and we can do it that way. So if I have two vectors, A equals ax, ay, az, and the vector b, bx, by, bz. I cannot say a times b. I mean, I can do a dot product. I can't multiply them together. I can do this, but I can't do just a, b, multiply them together. Because multiplication is a scalar operation. And we have two vectors which are not scalars. But there are two ways we can operate two vectors together, and the first is the dot product. And so a dot b, we use a dot right there, or also known as the scalar product because it takes two vectors and returns a scalar value. And it looks like this. ax times bx plus ay times by plus az times bz. That's it. So scalar, 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 they're all scalars, add them up. It turns out also that you can write a dot b as the magnitude of a times the magnitude of b times the cosine of theta, where theta is the angle between the two vectors. And so this is sometimes very useful to go backwards. Let's suppose I know the angle between them, I can find the dot product. Or if I know the two vectors, I can actually find the angle between them. Okay, last thing, the cross product. So the other way to operate two vectors is to do something that gives you a vector product back, and we call that the cross product. So A cross B equals C. And I didn't write it down because it's more complicated. But so this gives a vector. Now the first important thing about this vector, C, is that it's perpendicular to both A and B, and that the magnitude of C is equal to the magnitude of A times the magnitude of B times the sine of the angle between them. So this is where you get the right-hand rule from. I made this, it's Lego and tape. If I have vector A and B, then there are two vectors that are perpendicular to both A and B, and this is one of them, and the other one would be coming down here. But it's inherently a three-dimensional problem. So which one is it? That's where you take your right hand And if your fingers cross through A and then B, your thumb will point in the direction. So if this is A, that's B, this would be C. Okay. Now there's one other way to find A cross B, and it's to use the determinant of the following matrix. X hat, Y hat, Z hat, AX, AY, AZ, BX, BY, BZ. And that's going to be equal to C. So if I do the determinant of that matrix, I get C equals, I'm going to write it out the long way. So I'm going to expand about this first row right here, and then do the determinant of this. So it's going to be AX, BZ, AX, BZ, minus AZ, AY. See, I have bad handwriting. AY, BZ, minus AZ, BY. And now I'm going to expand about this row. Now, since this is the one position, it's going to be -1, or it's going to be, this is going to have a negative number right in front of it because of the way you do that determinant. So I'm going to actually do, this is going to be BX, I'm going to do the backwards, BX AZ minus AX BZ. And then finally, I'm going to expand about the Z, and I get AXBY minus AYBX. And so that's kind of complicated, but that's how you do that. Okay. Let's jump over to Python because we can do vector operations in Python, and it makes an actually awesome calculator. So this is Trinket Python. And the important thing you want to see here is GlowScript. So GlowScript is a module in Python that allows you to do a whole bunch of great things, but in particular, it has a vector class already in there. So let's just make some vectors. Let's say A equals vector 1, 2, 3. And now I'm going to print A. That's silly, right? But that's what I'm going to do. And there you go. So you see here, that's why I like that representation of the vectors using these angle brackets, because that's the way GlowScript Python does it, so it kind of matches up along with that. Let's make another vector, B. B equals, I'm going to make it crazy, vector 0.3 minus 0.42. Now let's do this. Let's say A plus B equals A plus B. So in Python, the print statement, you can put a string along with an actual operation in there. I don't have to have a variable. I can put an operation in my print statement. And you see here it printed out A plus B because I told it to. And then it actually added that. It said the component of 1 plus 0.3 is 1.3. 2 plus negative 0.4 is 1.6. And then 3 plus 2 is 5. I could say this. I could say C equals A plus B, and that could print C. If I want to put units, let's say they are units, I could just say units there too. If you want it to look nice. You don't have to make it look nice. You just need the number. So there you go. Now what if I want to do A minus B? And I'm not even going to make it as a thing, A minus B. That doesn't care, right? I can do that operation. That works fine. What if I just want to look at the Y component of C? I could do this. Cx equals C dot X. This is really useful in Python, right? I can just address the X component, or I'm sorry, I did say X. I said Y, but I wrote X. So it will only print out the Y component of C, which is 1.6. That's pretty cool. Okay, now let's delete that. Scalar multiplication. So let's just do print 3.5 times A equals 3.5 times A. Okay, so it multiplied each component by 3.5. Scalar, I'm going through these quick. Let's see, scalar multiplication, adding, subtracting, magnitude. You could do this. I could say a mag equals the square root of a dot x squared plus a dot y squared plus a dot z squared. Square root's a built-in function in Python, and print a mag equals a mag. And that gives me the magnitude of the vector. But there's a built-in function in Python that does it for me. I could also do this, print a mag equals, comma, mag is a function built into ClosesScript B Python. If I put a vector in there, it returns the magnitude of that vector. Same thing. The unit vector also, I could do it manually, but it's built into Python. So let's say print a hat, right? That's that hat over the thing, equals this would be norm for unit vectors, norm. So it'd be norm A, and it returns a unit vector in the direction of A. And you'll notice that should have a magnitude of 1. So if I do this, mag of norm A, if I take the magnitude of that vector, which is not a hat, it's 1, which I said it should be. So let's do this one more thing. Print A equals mag A times norm A. Right? So if I take the magnitude of that vector and then I multiply it by a unit vector in the same direction, I should get A. 1, 2, 3. Okay, now I need to do the dot product and the cross product, so that's pretty easy. So I have vector A and B. So let's say, let's delete this stuff because it's just getting in the way. Let's say D equals the dot product, which is going to be dot A, B. Print A dot B equals D. I could do it manually, right? I could do AX times BX plus AY times BY, but it's already built in there as a dot product. And you'll notice up here I get 5.5. What if I switch the order? What if I do BA? I get the same thing, because it doesn't matter the orientation of those components. I get the same thing. Now, what if I do the cross product? So that's just cross A, B. You got to give it 2 vectors. So it's going to be A, let's say, X cross B. And there I get a vector. If I switch the order here, A, B, I'm going to get the opposite. This is going to be 5, negative, negative. Okay. What if I do this? What if I do E equals 2 plus A? Print E. Can't add a vector and a scalar. It can't do it, right? You can't do that. So that's good. I really like that about Python. It prevents you from doing things you couldn't otherwise do. So I'm going to use Python in my calculations. When I talk about electric fields and magnetic fields and unit vectors, I mean, Python, if I want a numerical value, Python's the way to do it, because you don't have to do all the little bitty steps to find those unit vectors. So I would recommend that you do it. It even works on your phone. There are some calculators that have vector operations in them, but this is free, so I like this too. But okay, that was a lot longer than I thought, but there we go. Vectors. That was supposed to be a review. If you haven't seen that before, don't think that this is going to do it for you. And you know everything about vectors now. It takes time to get that up. I assume that you've already done some vectors, so this was a review. And I hope you find that useful. That's it.